Let's continue our discussion with amplitude and frequency modulation. Historically, these two schemes have been used extensively uh, in the old times for voice over communications and broadcasting. Now, this forms the this is from the chapter 6 of radio frequency electronics, the course textbook, John B. Hagen. Um, to understand these schemes, let us first see what this term modulation implies. You see, modulation is the variation of the amplitude or the phase or both of an otherwise constant RF carrier wave in order that the signal carries the information. And it could be a digital data or it could be a continuous analog waveform that is modulating an RF carrier. And the information could be represented by, it could be an audio signal, it could be a video signal. So what we have discussed previously, is that in a mixer, you have a multiplier, okay, and you have a message signal. Let's call this M of T, okay. So this is usually a low frequency signal. So this is M of T. This could be digital. This could be of digital nature if you're looking for a digital modulation scheme, or it could be of analog nature of continuum varying amplitude or whatever. If it's a continuous modulation, then you have a carrier signal, that's a CT, a high frequency carrier signal, and then you combine it, you mix it up to two signals. So at the output you have MT multiplied by CT, which results in the modulation of the message signal or the encoding of information, and by how the information is encoded into the carrier for transmission. Well, you are varying the amplitude or the frequency. So look over here. For example, you have the digital data. Okay, so let's call this as M of T. Okay, you have a digital M of T, which is a variation of ones and zeros. So this could be, for example, 1, 1, and this would be 0, 0. Okay, this is 1 where the data is present. Then you have 0, 0, so 1, 1, and this thing continues. Okay. Now, when you combine this with the carrier signal, which is a high frequency signal, okay, having a certain amplitude. So what you are doing is you're varying the amplitude. Okay, so without varying the frequency, you are encoding the information into variation of the amplitudes. So, for example, when you have the binary data that is high, you are letting the carrier to pass through. Okay, so you're letting the carrier pass through like this. When there is no data, the output is 0. So you have a series of on and off states. So this is a simple case of binary shift by binary on and off keying. So for example, when there is data, the switch is on, so you have the carrier sent through. If there is no data, there is 0, then the output is 0. So for that, again, it is on, then off, on, off, and this trend continues. So this is a modulated scheme. This is known as, this is an ASK waveform. This is an amplitude shift key waveform. So you have a digital waveform and digital message signal, and that's how you encode a continuous RF signal. So amplitude modulated and frequency modulated, well, they are continuous. They use continuous modulation schemes. For example, in amplitude modulated scheme, you have the amplitude that is being varied continuously. In digital AM or binary AM or amplitude shifting like this over here. So this, you see it over here, you have the simplest form of AM, that is on-off keying. So this binary digital AM, which is full on when data is on, and it is full off when the data is 0. So it can be produced by a simple switch, right? So it's like a telegraphic key which is in series with an antenna or a power source that is being used for antenna, which is being used for the transmission of the modulated signal. So in the continuous schemes like amplitude and frequency modulation schemes, you don't have a finite modulation states. Okay, you don't use you have a continuum of variation in amplitudes or frequency with respect to the audio or the message signal. So, for example, if it is a continuous AM or a continuous FM, the amplitude or frequency in case of FM is being varied with respect to the amplitude of the audio or the message signal. So there's a difference in digital and analog modulation schemes. Okay, here's a simple. I've already talked about this. This is a ASK generation method. So what it does is you have a carrier signal. Okay, you have a carrier signal, and then you have a unipolar binary message signal like this, the one we have seen before, and it's a simple switch. Okay, so it is combined over here with the sinusoidal carrier through switching, and what you have at the output is you will either have a high output or you have a low output when there is no data. Then a high output, okay, you allow the RF carrier to switch through, or a low data. So there are only two states over here, simply on and off keying. So the output will be a carrier at the high input, and when the input is low, the switch opens. So there is no voltage that appears. Hence, the output will be low. What we have seen earlier. So this is the basis of how you are varying the amplitude of the carrier. You see, either you are allowing the carrier to pass through. There's or either you're not allowing. Yeah, the switch is open, so there is no data. Okay, so it's like a binary ASK scheme, binary amplitude shift scheme. Simple on and off keying. So generally, ASK, like any other digital modulation schemes, ASK uses a finite number of amplitudes. Okay, and each assigned a unique pattern of binary digits that is the symbol. Okay, so the data rate depends on the symbol rate, the bandwidth, or you might want to call it. So this is the number of digits that you are going to assign with each finite amplitude in ASK modulation scheme is the symbol. So usually each amplitude encodes an equal number of bits, and each pattern of bits forms the symbol that is represented by a particular amplitude. And what happens in the demodulator is that demodulator knows what symbol is being transmitted, and then it simply matches those symbol with a lookup table or what it knows about the symbol to recover the original amplitude. That's what the demodulation is. So the demodulator, which is designed specifically for a symbol set used by the modulator, so it knows the symbol set that is being used by the modulator, and then it uses this symbol set to determine the amplitude of the received signal and then maps it back to the symbol it represents, thus recovering the original data. So that's how the modulation and demodulation is done. But in this particular, or you have this is since we are talking of amplitude shift keying, or if you are having a let's say a continuous amplitude modulation, the frequency and the phase, the other two parameters of the carrier are kept constant. You see, for example, over here you have a continuous unmodulated waveform. It's a RF carrier signal, and as the for example, for a modulating signal, as the amplitude is varying for an audio signal. So here you see you have a sort of an envelope over here. You see, so when the amplitude is high, the modulated envelope is high. The envelope actually catches the shape, so the envelope is like this. Okay, so as the amplitude is high, the output AM modulated waveform, the amplitude is high. That's how it looks like in the time domain. When the amplitude is low, so you have a low variation of amplitude. When the amplitude of the modulating signal or the message signal is high, the modulated waveform has more strength. Okay, so that's how you are producing the variations in the amplitude, and this variation is continuous. Okay, so for example, the instantaneous amplitude at any instant of let's say this T1. Okay, we have another instant. We have another instant over here. It's T2, or we have another instant over here, T3. Okay, so these two instances, the strength of the AM signal at T1, T2, T3 is different because it depends on the instantaneous amplitude of the modulating signal. So these two are different. These three are different. Okay. So with AM, the frequency of the carrier wave is constant. That is important. So you see over here the zero crossings are the same. Okay, so zero crossings the same means you are not varying the frequency or the phase of the signal. So it's only the amplitude. The variation is only in the amplitude. So zero crossings of the RF signal are equally spaced, just as they are for the unmodulated carrier. Okay, so the frequency remains intact. It's amplitude modulated signal. Similarly, if you have an FM scheme, the simplest FM scheme, for example, if you have a digital data, you are considering you have digital data that is modulating RF carrier. You have digital then you have a digital, for example, frequency shift keying. So for example, you have a data like this, some binary data 0, then you have some ones, you have zeros. Okay, so what happens is, for example, over here you have a certain frequency f0. Okay, and once you have the data, then you might have a frequency, let's call f0 plus a certain deviation. I call it delta f maybe. So for example, if this f0 was to be 10 kilohertz, then when the data is present, then delta f, whatever it is, 4 kilohertz or 5 kilohertz, you have a 15 kilohertz variation over here, so the frequency is more over here, and then it becomes low like f0 again. Okay, so this is a form of binary f plus k. So what is happening is, for a binary f plus k frequency shift keying, the control voltage is only two values. Okay, so you have again finite states, two states of modulation. So one produces f0 and the other is producing f0 plus f plus delta f when there is data. Okay, so FM broadcasting uses a continuous range of frequencies. In a continuous FM, you have a continuous range of frequencies, and the instantaneous, again, instantaneous frequency is determined by the amplitude, just like in continuous analog. Okay, so for example, at time t1, t2, t3, the amplitudes are varying continuously. It depends on what the amplitude of the microwave signal is, so that decides the shape or the envelope. Similarly, if you have a continuous FM, you're not looking for a digital FM. For a continuous FM, you use a continuous range of, the variation is in the continuous, it is continuous the frequency that is being varied for the RF carrier. The instantaneous frequency is determined by the amplitude. Perhaps this figure shows better picture of what's going on in FM. You have a carrier signal. Okay, so the amplitude is the same, and you see that even in the modulated output, the amplitude is the same as that of the carrier signal. So what you are doing is you are varying with respect to the amplitude. The amplitude is high, so you have more frequency. So the instantaneous frequency is depending on the amplitude. You are varying. So over here you have low frequency. So you have low frequency, then you have high frequency. Okay, then again you have low frequency. So while you have high frequency, the amplitude is high over here. Okay, then it's low. So you have this trend over here. So it's low frequency. Then again the amplitude is high. So amplitude is high, the frequency is high, the amplitude is low, the amplitude of the audio signal is low, or the message signal is low, the frequency is low. So that's the trend. So in frequency modulation, type of modulation where the information message signal is transmitted over a carrier by varying its frequency in accordance with the amplitude of the message signal. So depending on whether it is FM or AM, you are varying the either the amplitude or the frequency of the carrier signal. That's how you encode, or that's how you send the data. By changing one of the parameters of the carrier signal. Okay. Now let's have a closer look at what happens in the amplitude modulation in both time domain and the frequency domain. So amplitude modulation is that was one of the first schemes used for radio broadcasting, and it's still being used in long wave, middle wave, and short wave radio broadcast. Oh, well, long wave, middle wave means for long waves, the band extends from 153 to 179 kilohertz. Middle wave means you have it up until 1700 kilohertz. Short waves are small wavelengths, 75 to down to 11 meters. Okay, 75 meters to 11 meters. Those are short wave radio bands. So what happened in the time domain is, you see, without modulation, when the speech or the music is silent, you have no modulating signal. So M of t is 0 over here. M of t is 0. So what you have at the mixer is only the carrier. You are left with the carrier signal. So the voltage, in case of when the message signal is 0, the voltage being applied to the antenna is a pure sine wave at the carrier frequency. Okay, if you don't have anything to mix, well, you only have the carrier that is coming over here, right? So this is the carrier signal, and well, so you only have the carrier. The power of the radio station is defined as the transmitter output when the modulation is 0. Okay, so for example, if you're going to modulate it in the presence of an audio signal, you know that the amplitude of the carrier is changing, and depending on that envelope, For example, for a carrier signal, you have a maximum amplitude of Vm. Okay, it's like Vm sine. Let me write this down. We have sine omega ct. Okay, and so you see that the output power is, let's say, the power out, but in the absence of message signal, is Vm square over 2. Okay, it's Vm square over 2. That's the power of the transmitted carrier without modulating signal. But if you have a modulating signal, and let's say the maximum amplitude is 2 Vm, let's say, okay, that means twice what we had previously, then it's like Vm square. Okay, it's like twice Vm square. That power output becomes twice Vm square power output. Why it is twice Vm square? Well, you see, for 2 Vm, that is 4 Vm square over 2 V square over R. So the power output is 2 Vm square. That is 100% modulation. So that means it requires how much? It requires 4 times more power, 4 times more power from the antenna, if the modulation is as such. Okay, for 100% modulation, 4 times more power. For example, if the antenna system is configured for 50,000 watts of broadcasting information, then with modulation it should be able to handle 4 into 50,000, that is 200,000 watts of power transmission. So it depends. If you're defining the transmitter output, when there is no modulating signal as the power of the radio station, then the presence of audio signal, since it changes the amplitude of the carrier, then one has to see how the envelope varies or what's the amplitude, and then see if that there is no breakdown with that power, and if there is a power handling capability as such for the modulating signal. Okay. Anyways, okay, now this is a hypothetical AM transmitter. So you have a microphone. Okay, your microphone that gives a continuous range of amplitude. It could be a variable resistor, let's say. Okay, you can model this variable resistor as well. Okay, which gives varying currents or amplitudes. And so what we are doing is we are interested in this message signal. This is a continuous message signal to modulate a carrier signal of a certain frequency. In this case, you see this, for example, these nodes. The first node is your message signal. So over here I have V1. Okay, so this shows 3.6 times 2 pi 21t, and then I have another tone at 62t. So I have actually 2 spectral components. Okay, I have near to DC, I have 2 spectral tones. This is the time domain variation of the input, and that is the frequency domain. This is 21, and that is 62. Okay, so I have 2 tones. Now the carrier signal is at 1000 hertz. Okay, so I have far away 1000 hertz modulating signal. So this is 1000. Okay, so 1000. This is okay. This is DC, and this is 1000. And again, you have it at minus 1000 as well. Okay, it's a real signal, so the spectrum of the real signal is symmetric. So that's always the case. Similarly, I've shown the single sidebands over here. You will have minus 21, and you will have minus 52 as well. Okay, so 2 more sidebands, symmetric spectrum, minus 21 and minus 52. Now, as you have seen, or if you would appreciate from the last chapter of mixers, what happens is once you mix MT with CT, so what happens at the output? So for example, if you wanna so this 10 is a DC bias term over here. If you want your audio such that it is always positive, okay, so if you clamp this to 10 volts, you have the minimum variation at minus 5, so it's always positive. So you will have at the output, this is 10 times V2T plus V1 and V2T, so it's 10 times V2, okay, plus this will be V1 plus V2 So these cross product terms, time domain terms, are going to produce modulation, double sidebands. Okay, so in transform domain, what you will have is around 1000. You will have two spectral shifts. Okay, upper sidebands, lower sidebands, and this is what the information is that we are transmitting. So the output is like this in transform domain. So for example, if this is 1000, okay, if this is 1000, then this is how much? This is 1021. Okay, this is 1062. Okay, and similarly this is 1000 minus 21, which is 1079. Okay, then 1000 and sorry, not it's 979, it's not 1. And similarly you will have 1000 minus 62, which is 938. Okay, so you will have 930 hertz. So in time domain you have this variation. Okay, and if you see this variation, the envelope of the signal, it is exactly looks like what we have. This morphology of the envelope, the shape of the envelope is what we have over here, right? It's the message signal. It's the message signal that is riding over a high frequency carrier, and the variation is only in the amplitude. That is how you are modulating it. That is how you are modulating it. The variation is only in the amplitude, and that's how you are modulating the amplitude of the carrier. Okay, and you're not varying the frequency. The frequency remains intact. Okay, the zero crossings are the same. The zero crossings are the same, so the frequency stays constant. So that's how you shift the spectrum at 1000 and minus 1000. Okay, so this mixing is what the modulation constitutes. Okay, in the transform domain. So what happens next is if you want to this is how you extract back the message signal or the envelope at the receiver side. You consider this hypothetical Am receiver. Okay. So what you have is in the first instance you look at this nonlinear circuit element diode. So what it does is, for a positive voltage V3, for this is your V3. So only the positive half cycles are going to this diode is going to let through the PN junction. When the PN junction is forward biased, you have the positive variation, you don't have any negative variation. So V3T, it's V4 is V3T actually when V3T is greater than 0. Otherwise it's 0. Okay, so this is the output at the node 4 here. Now the next section constitutes a low pass filter. Okay, you see you have a low pass filter over here. This is a low pass filter. What this low pass filter does is it does a running average. Okay, on V4. So what it does is it averages. This is a running average operator. Okay, so you're taking 40 samples and then you have this divided by 1/40. So it's just smoothing out the high frequency. It's averaging the signal. What it does is you see it's since the low pass filter at high frequency the capacitor shorts and nothing comes out. At low frequency this is open, so it lets through. So what happens is that since the diode is conducting in the positive half cycle, okay, diode is letting through the positive half cycle, and when the negative comes, the diode is open circuited. Okay, so it's like this. The capacitor is going to be charged up in the positive half cycle, then it discharges, then positive cycle charges up, then it discharges. Okay, charges, discharges, and you see this continues. This trend continues. Okay, so it's like this. So you have some variations like this. It's not very smooth, but it's an averaging operator again. Okay, so you have some variations like this, but again, that's how you are recovering this signal at the output. This is 5, and then the C is a coupling capacitor or a bypass. This is a coupling capacitor which removes the DC component. Okay, so we are looking before this capacitor. So we have a DC over here. So after this capacitor, there is no DC, and you can recover your original message signal without any bias term. Here is a MATLAB simulation which is showing what happens in the, so these simulations shown in the textbook were in the time domain. So let's have a look what happened in the frequency domain. So I constructed this simulation again in MATLAB for to see what happens in the frequency domain. You can use frequency Z to get the magnitude of the phase spectrums. So for example, over here in the lower graph, you are looking at the normalized frequency, the amplitude, and dB versus the normalized frequency. See, the high frequency is 1. Okay, so it depends on what sampling frequency you are choosing. You can always denormalize the scale. Anyways, this is the same signal. Okay, what we had earlier. So V1 is minus 5.3 cosine 62 2 pi 62t, and then 3.6 sine 2 pi 21t. So this is the same. I've reconstructed the same modulating signal over here, consisting of two. You can see over here there are two peaks around the DC. Okay, around the DC. So you have two peaks. So it's just like this. So we are talking about these two peaks over here. So we have them. Okay, but again the scale is normalized. Okay. Now this is the high frequency carrier. Okay, so you see the 1000. This is 1000 hertz, and in the normalized scale, this happens at around 0.2 normalized frequency. So once these two are mixed, so for example V3 is V2 multiplied by V1 plus 10, which is the bias term. You see that those two, these two frequency tones are simply shifted around 0.2, which is the frequency of the carrier. So you see this is a lower sideband, this is an LSB. Okay, this is LSB. This is my carrier C, and this is my upper sideband. Okay, this is my upper sideband. So you see the modulation has occurred, and that's the envelope of the signal. So this is the transmitter side. So next, once you are you pass it through a diode, you only have the positive excursions of the signal. There's no negative half cycles. You have the repetitions of the modulations. Okay, this is the frequency spectrum at the output of the diode. So you're not interested in the replicas of those modulated signals. This is the original modulated signal, and this is the replicas that are occurring. So they can be band pass filtered out, and then it happens on the DC as well. So if you are going to low pass filter it to after an RC low pass filter or in MATLAB, what you can do is what I did is to averaging. I used the moving averaging filter to recover the envelope. Okay, just like what you have in the envelope detector, you have an RC analog RC. So the capacitor charges, discharges. You can set a very high time decaying time constant. So it doesn't decay very fast. Okay, so it decays slowly. You can have the signal like this, and then in the transform domain, you see that the envelope detector output is it almost recovers the same sideband over here. Okay, same sideband over here. So this is how you do the demodulation of the AM, or recover the original message signal from the AM modulator signal. So this is your copy of original message signal.